First of all, let's begin by looking at factorial notation. That is the actual definition of factorial notation. 0 factorial is defined to be 1. And then to get n factorial from there, you just multiply it by the next number. So what can we conclude from that? Well, 1 factorial then must be 1 times 0 factorial, which we've defined to be 1, so 1 factorial is 1. 2 factorial becomes 2 times 1 factorial. 2 times 1 is 2. 3 factorial is 3 times 2 factorial. 3 times 2 is 6. 4 factorial, and so on and so on and so on. And we come up with our definition for n factorial, n times n minus 1 factorial, which would be n times n minus 1 times n minus 2 factorial, which would be, and if we kept what we call rolling out the factorial, eventually we would get to 1. And effectively what we've ended up with, well, hang on, it's all those consecutive numbers multiplied together. So that's n factorial. Now why think of it like that? If I had to cancel something like this, 12 factorial, 9 factorial, I can roll out the 12 factorial until I hit 9 factorial. So 12 times 11 factorial, which becomes 12 times 11 times 10 factorial, which becomes 12 times 11 times 10 times 9 factorial. Now the factorials cancel, so alright, that one is 12 times 11 times 10. 16 factorial, well, if I'm going to roll it out, I'll roll it out to the biggest one. So 10 factorial is what I'm going to cancel. And that leaves me with 16 all the way down to 11 on the top. The 7 factorial is still on the bottom. And that's where we get to do some cancelling. So what do we got here? We can say 7 2s are 14. That cancels. So now I have this fraction, but there's still more cancelling to be done. 5 3s are 15. That'll cancel. All right. Now, what can we do? Well, the 6 will go into the 12 twice, so I can do that. And the 4 will go into the 16 4 times, and I end up with that multiplication. Oh, eventually, there we go, 1,144. You know, think, well, hang on, I've got a calculator. Why would I worry about that? Because when I get something like this, I can't do that on a calculator. I've got 1 on k factorial plus 1 on k minus 2 factorial. There is a common denominator there of k minus 2 factorial, because if we rolled out the k factorial, it would actually be k minus 1 times k minus 2 factorial. That therefore means, well, the 1 on the k factorial stays as 1, but the k minus 2 factorial I've multiplied by k minus 1. Tidying it up, and that's the best I can really do as far as cancelling goes, because k squared minus k plus 1 I don't think factorises nicely. Well, not with neat integers that would cancel with that factorial. So that's factorials, which is going to come in really handy in this combinatorics. We start off with a very basic idea called the basic counting principle, which simply says this: if one event can happen in m different ways, then after that another event can happen in n different ways, then the number of ways the 2 events could happen would be m times n. I'm going to roll 3 dice. How many ways could they fall? Okay, well, it should be 6 times 6 times 6. Why? By the basic counting principle. Well, the first dice, when I roll that, it's got 6 possibilities. Then I roll the second one, it has 6 possibilities. I roll the third one, it has 6 possibilities. So there are 216 possibilities there. So generally, the number of ways of arranging n distinct objects with replacement, that's the key with all this combinatorics, it's with replacement, in k different ways would end up being k to the power of n. I had a dice, could be rolled in 6 different ways, 3 times 6 to the power of 3. Well, how many ways could all 3 dice show the same number? Well, it'll be 6 times 1 times 1. So again, by the counting principle, look, if you roll the 3 dice all at the one time, it's no different to getting 1 dice, roll it, next dice, roll it, next dice, roll it. So you can think of it like that, even though you might be rolling all 3 at once. And I'd say, well, that first one, then there's 6 different things that it could do. But now the second one, I want it to show the same number, so it only has 1 possibility. And then the third one, I want it to show the same number, so it only has 1 possibility. We end up with 6 different ways. And I guess logically that makes sense, because we're saying how many ways can all 3 show the same number? Well, they could all show 1, or they could all show 2, or they could all... There's going to be 6. That then brings up the next logical question. Right, why did we do those two? Well, what would the probability be that all three dice show the same number? And you might remember from your probability theory, it's the number of outcomes in what we're interested in looking in over the number of total outcomes that we could have. So in our one, the 6 over 216, which is 1 in 36. Here's an older HSC question now. Mice are placed in a maze. It has 5 exits. Each mouse is equally likely to leave the maze through any of those 5 exits. And to help us out, they've told us, thus the probability of any given mouse leaving by a particular exit would then be 1 in 5. 4 mice, A, B, C and D, are put into this maze and they behave independently of each other. What's the probability that A, B, C and D all come out the same exit? Well, the total number of possibilities would be 5 to the power of 4. There's 5 different possibilities for the mouse to go at, and there's 4 different mice doing it, so 5 to the power of 4, 625. But if I want them to go through the same door, again, it doesn't matter if they all leave at once, or we think of it as, well, one mouse leaves, then another mouse leaves, and so on. So I'm going to think of it that way and say, well, look, that first mouse, they could go through any door, but I want the other mice to go through the same door. So they now only have one choice. So there's 5 different possibilities there. Probability, they all use the same exit, then becomes 5 on 625, which simplifies down to be 1 on 125. But then they said, well, how about this? What's the probability that A, B and C come out the same exit and D goes out a different one? So the number of ways A, B and C can use the same exit, and then D uses a different exit. So I'm going to imagine D left first. Now D could go through any door. It's got 5 possibilities. Now the next mouse, let's say it's A, has got 4 doors to choose from. It has to go through a different one. But then B and C have to go through the same door. I said as D there, actually it should have been as A, but through that same door. So there are 20 different ways they could go out in that situation. 20 over 625, 4 in 125. But then they asked, well, what's the probability that any 3 of the 4 mice go out the same exit, so it doesn't have to be A, B and C, and the other mouse goes out a different exit? We just worked out the situation that D uses a different exit to the other 3. But that's just one of the mice. It's all equally likely. So the probability that A goes through a different exit to the other mice must also be 4 in 125. Probability of B doing it must also be 4 in 125. Probability of C doing it must be 4 in 125. Therefore, the probability that any of the mouse uses a different exit to the other 3 must be 4 times 4 on 125, 16 on 125. But wait, there was more. What's the probability that no more than 2 mice go out the same exit? Now this uses an idea in probability that you might recall the complementary event idea. Sometimes it's easier to work out the probability of things not happening rather than the probability of things happening, and then we just subtract it from 1 because we know all the probabilities must add up to be 1. Now in this case, we have already worked out the probability that they all go through the same exit. We have also worked out the probability that 3 of them use the same exit and one goes out a different one. So if you think about it, the opposite to that, so the other thing that is that no more than 2 go out the same exit, because we've worked out the 3 and the 4. So if I subtract those probabilities we just worked out, I get my answer. So that's the basic counting idea, which leads us into this idea of permutations. What is a permutation? It's simply an ordered set of objects. The order of things happening matters. So it's an arrangement, if you like. Going to look at a few cases. The first case, ordered sets of n different objects from a set of n objects. Basically, I'm going to use all the objects. I'm just going to arrange all the objects. That's what this is saying. So if I have n different objects, so over here there's a pile of n different objects, and I want to line them up out the front here. How many ways could we do it? Well, I'll go and grab the first one. I've got n objects here to select from. So, all right, I'll grab them. Bang, I've grabbed that first one. put them down first. I'm now going to get the next object. There's now n-1 objects left. So n-1, you'll go in the second spot. Go back to the pile, there's now n-2 objects, and I could keep doing that until I get to the very last object. Don't worry, we're not leaving you out. Go and join the queue. So we get down to 1. And look at what we've created. That was, in fact, our formula we saw for n factorial. That makes life very easy. If I just want to arrange a certain number of objects, it's just that number factorial. That's how many ways I can do it. Now, in how many ways can 5 boys and 4 girls be arranged in a line if no restrictions? Well, it's just 9 factorial, because I don't care it's 5 boys and 4 girls. As far as I'm concerned, it's 9 people. I'm just arranging 9 people in a line. 9 factorial ways of doing it. See, the advantage of using this combinatorics idea is that I don't have to now draw up a sample space. Imagine if I had to draw up a sample space for all those possibilities. 9 factorial? That's a big number. I don't want to be writing all of those out. There it is indeed. Whew, that would take some time. 362,880. Okay, but we like to put some restrictions on things. Well, what happens if this queue, we want a lovely pattern. We want the boys and girls to alternate in our line. So always think about the restrictions to the problem. What is the restriction? Now, the first restriction here might not immediately be obvious, but the first restriction is that. Do I start with a boy or do I start with a girl? I have to start with a boy, because there are more boys than girls. If I started with a girl, then it would be impossible to then create an alternating pattern. So there's only one way I could start. Now, if there was an even number, then I would say, okay, there's 2 ways I could start. Okay. I will now go and arrange those boys. Okay, there's 5 of you. Go line up, 5 factorial, but oh, by the way, can you just leave a bit of a gap between each of you so the girls can fit in, and we'll get this lovely alternating pattern. So they've done that. And now we go to the girls and say, okay, girls, line yourselves up and just fill in those gaps. 4 factorial. Yeah, I could have achieved it a different way. I could have said, we have to start with the boys. 5 ways of doing it. Next one has to be a girl. 4. Next one has to be a boy. 4. Next one has to be a girl. 3. Next one has to be a boy. 3, and so on. You'd end up with 5 times 4 times 4 times 3 times 3 times 2 times 2 times 1 times 1. Well, that's exactly the same as, hey, let's not make things hard for ourselves, because it's still 5 factorial times 4 factorial. 2,880. Again, now brings up the logical probability question from that is, well, if I've got this situation, what's the probability that when they go and randomly line themselves up, what's the probability that they end up alternating? Number of possibilities, 2,880, over the total number of possibilities without any restrictions, and that turns out to be 1 in 126. And we can do that without drawing tree diagrams, without drawing up a sample space, and so on. We get our answer. What about a different restriction? So 2 of them are really good friends, and they want to be together. They've got to be together. I'll look after that first. And I'll say, well, righto, you 2 want to be together. Just organise which way round you want to go. So 2 factorial, I've looked after that restriction first. Now, as far as I'm now concerned, they are no longer 2 people. They are just 1 object. Because once they've worked out which way round they're going, they're staying in that order. So I'm no longer arranging 9 objects, I'm now arranging 8 objects. That group of 2, and then the 7 other people. We get 2 factorial times 8 factorial, 80,640. But let's say we don't want to use all of the objects. So that's what I'm now saying. K is less than n. I'm not going to use all of the objects. How does this change the problem? Okay, we still have our pile of n objects over here in the corner. We're going to line them up, but I'm only going to use some of the objects. Well, there's still n possibilities for the first one. There's still n-1 possibilities for the second one, n-2 for the third one, and so on, until I get to the last one that I want to arrange, so the kth object. How many do I have to choose from? Well, n minus k plus 1, because have a look. The first object was, if you like, n-0. The second object was n-1. The third object was n-2. Therefore, it's logical to assume that for that last object, it's going to be n minus k plus 1. Well, we can make that simpler by making it harder. So I'm going to multiply top and bottom by this lovely fraction here, which of course is 1. Why on earth do that? Because what we've got then is on the top of the fraction n factorial, on the bottom of the fraction n minus k factorial. Think about that fraction. There's a good reason why it ended up like that. We were going to arrange n objects. So what this is saying is, well, on the top of the fraction, if I had arranged them all, there would be n factorial ways of doing it. But over there in the corner, I left n minus k. I didn't use them. So actually, I don't care about the arrangements of those ones I left behind. So I'll divide by those arrangements. I don't care about those arrangements. So that's why we divide by the n minus k factorial. So n factorial, number of ways we could arrange all the objects if we were going to, divided by the number of ways I could arrange the objects that I didn't bother using. There's a lovely button on your calculator. We'll work that out straight away. That's our permutation. There's our notation for it, NPK. NPK. I think of most of them it's on the multiplication. On the multiplication. Let's look at some examples. Sometimes it's just easier, by the way, to just go, what's n factorial divided by n minus k factorial? Just work that out. Well, seeing we're doing a problem, let's use the word problems. How many 5-letter words are possible? Possibly a better way of saying is, how many 5-letter arrangements are possible? Because as far as we're concerned, any 5-letter combination is a word. It might be a nonsense word, but it's a word. If there are no restrictions, then there are 8 letters. I'm going to use 5 of them. So 8p5, which if you press the buttons on your calculator, you'll get 6,720, or if you prefer, it's 8 factorial on 3 factorial, which means the 3 factorial will cancel into the 8 factorial, leaving you with 8 times 7 times 6 times 5 times 4. There's our answer. But hang on, I only want words that begin with the letter P. Look after the restriction. There's only one way I can put that P. It's at the front. Now, it's like I've now got a new question. How many words, 4-letter words, can I create from the word problems? P's gone. Oh, that's 7p4. From the 7 letters, I'm going to use 4 of them. 840. All right, make it even more interesting. Well, P is included, but this time it's not going to be at the start of the word. And oh, by the way, I don't like the letter M, so we're going to exclude that letter. Look after the restrictions. Well, now there's 4 places P can go. It can go anywhere, just not at the beginning. So there's 4 spots I could put P. But I'm not going to use M, so now the question becomes, how many 4-letter words from Robbles? M's gone, P's gone. That's 6p4, 1,440. 6 people are in a boat. It's got 8 seats. 4, they weren't very good at spelling, by the way. 4 on each side. What's the probability that Bill and Ted are on the left side and Greg is on the right side? I can't remember which one's which. One's port, one's starboard. I can't remember. We'll work out. It's a probability question, so I need to know the total number of arrangements with no restrictions. That'll go on the bottom of the fraction. And that'll be 8p6. There are 8 seats. We're going to use 6 of them. Okay. Now, the possibilities I'm looking for. Well, Bill and Ted, look after them first. They're only going on the left-hand side. So of those 4 seats, I'm going to use 2 of them. 4p2. Now Greg comes along. Oh, I want to sit on the other side. Okay. Of those 4 seats, I'm going to use 1 of them. That means I've used 3 seats, leaving me with 5 seats, and I've now got to use 3 of them. So 5p3. Multiply all that together, 2,880. Therefore, the answer to our question we were looking for, the probability of that happening, 2,880 over 20,160, which is simply 1 in 7 when we cancel down. HSC question. Sophia has 5 coloured blocks: red, blue, green, yellow and white. She's going to make little towers. So 2 blocks could make a tower, 3 could. In fact, any number of blocks could make a tower other than 1, because 1 block would not be a tower, it'd just be a block. How many different towers could she make that are 3 blocks high? Now, because they are different colours, the arrangement that we put these blocks together are important, because it will be a different tower. One tower might go red, blue, green, another tower might go green, blue, red, yeah, it's the same colours, but it's a different tower. So 5p3, 60. Well, what about in total, how many towers? All right, well, we could have 2 block towers, 5p2, 3 block towers, 5p3, 4 block towers, 5p4, and 5 block towers, 5p5, which would be 5 factorial, 120. Add those up, we get 320 different towers that we could make. Okay, let's say a lot of theory to start off with. There's some questions we can have some real fun with.